I'm Tyler Hashimoto.
I'm Jacob Landsiedel, and this is Lab 4, Optical Beam Collimation and Testing Radius of Curvature.
For the ideal Keplerian beam expander, we'd use a Newport M40X, which has a numerical of 0.65, which will allow us to fill the collimating lens, the 2-inch diameter collimating lens. We have a 7-micron pinhole and a collimating lens that has a focal length of 285 millimeters. However, we didn't have this lens and we had trouble with the working distance of this objective, bumping the pinhole before we were able to get a clean beam with the spatial filter. So we used this setup instead. And this setup used the M20X 0.4 numerical aperture objective, which we only had the 300 millimeter collimating lens. This led to an underfilling of the 2-inch collimating lens, about 13.43 millimeter radius, causing an expansion ratio of 33.33. And that leads to a smaller beam diameter, which will lead to a decreased shear plate sensitivity.
We shine the laser through the spatial filter, then through the collimating lens before going to the shear plate. As you see here, the fringes are parallel with the laser because the beam's collimated, and the fringes appear slightly aberrated. They're more aberrated if the collimating lens is not in the correct position, and the correct position is when the plano side is facing the laser. So therefore, we will try the lens in 2 different positions to see which one is better. This is the second configuration we tested. As you can see, it's clearly far more aberrated than the first orientation, therefore the first one has the plano side facing the laser. Light comes in here as before through the beam expander, and then it goes through the shear plate, transmits through, goes and reflects off the mirror, reflects off the shear plate again, and goes to the window up top. We see here the distance between the fringes, called the fringe spacing, is d, and the angular deviation is alpha. Using this in our other required values, we used these formulas to first find r, which gave us rm, the radius of the mirror, which in turn gives us fm, the focal length of the mirror.
Measuring the fringe spacing with the calipers, and then we'll also be measuring the angular deviation with the protractor. And then we will take the mirror itself and move it down the optical axis, and we'll repeat the measurement. The last measurement we need for this test is the shear distance, where we move the collimating lens towards the shear plate, and we can find the distance between the 2 beams.
As always, the light goes through the beam expander, and then this time we have the test lens right here instead of the mirror behind the shear plate. And so it goes through the test lens, and then we flip the shear plate around, so now it just refracts straight into the window, and we measure the same things that we measured before, and this time we use the equation F equals R plus L to find the focal length of the lens. This experiment is just like the last one, except instead of having the mirror after the shear plate, we have the test lens in between the collimating lens and the shear plate, and we measure the fringes using the same methods as before.
So to test the curvature of the curved mirror, the light will come through the Keplerian beam expander, through the wedge shear plate, which is now oriented so the light coming back from the mirror will be reflected up into the window. Through a reference lens, this was measured at 250 millimeters, and then to the position 1, where the focus of the light is coming from the reference lens to the front surface of the mirror. We'll record the measurement here, and then we'll push the mirror back until we find where the rays are normal to the mirror plane, which will reflect back through the focus, back through the reference, and be collimated, and we'll read it off the shear plate as well. And the distance I moved the mirror from the position 1 to position 2, I measure that, and that becomes my radius of curvature, which was found to be 199 millimeters, plus or minus 5 millimeters. This radius of curvature is smaller than what our last test was previously able to measure. So with this one, we have collimated light hitting the shear plate. The shear plate's oriented to see the light coming back from the mirror. We have the reference. We'll move the mirror to where the light comes and focuses, and it'll send the light back collimated. And then we continue to move this distance back until the wavefront is normal to your mirror surface. And for non-wedge shear plates, when the incoming beam is collimated, you'll get a constant OPD, which will lead to a null fringe. When the beam is converging or diverging, you'll get vertical fringes, but you won't be able to tell whether it's converging or diverging.
Just like the unwedged shear plate, the OPD in the X direction is constant, and so no fringes are caused by that. However, in the Y direction, the OPD is not constant. As you clearly see the wedge here, obviously the optical path length is shorter up top and longer on the bottom. These differences cause fringes or interference patterns, which is what you see in the window on the top of the shear plate.